The Euclidean algorithm is going to give us a process for determining what the GCD is of two given numbers. We might have some fairly large numbers. Consider the pair of integers 343 and 280. Well, the guess and check method of finding all the divisors and then picking the biggest one, that could take a while, especially if you're working by hand. So the Euclidean algorithm is going to give us a process that will allow us to determine something like the greatest common divisor of these two numbers. The statement of the Euclidean algorithm is that if I have two integers, a and b, and I'm going to assume here, for simplicity's sake, that a is non-negative and that b is strictly positive. Although this does generalize, we can consider negative integers as well. Well, from a previous video, we saw that I can find some number q so that a can be written as b times q plus a remainder r, and we know that r is at least 0 and strictly less than b. Well, now I can apply this again to the numbers b and r. In particular, I can write b as r multiplied by some other integer q sub 1, say, plus a remainder r sub 1, and now I know that that remainder r sub 1 is strictly bigger than 0, at least 0 and strictly less than r. And I can do this again with r and r1, so then I get that r is equal to r1 multiplied by q sub 2 plus some new remainder r sub 2, and I know that r sub 2 is at least 0 and strictly less than r sub 1. And this pattern continues, so in general I'm going to have a term looking like r sub k being written as r sub k plus 1 multiplied by q sub k plus 2 plus r sub k plus 2, where 0, r of k plus 2 is going to be at least 0 and it's going to be strictly less than r of k plus 1. Okay, so big whoop. It seems like I'm just going in circles, reusing this lemma. But the point is, notice that each time my remainder terms, my r sub 1, r sub 2, they keep shrinking. They keep getting smaller. And so the point of this theorem is that eventually this pattern bottoms out and we get to a point where we have some t, so that r sub t minus 1 will be equal to r sub t multiplied by qt plus 1, and the remainder is going to be 0 in this case. So eventually we're going to get some pair of numbers which are divisible. There's no remainder term happening. And the claim of the Euclidean algorithm is that this number r sub t is actually going to be equal to the greatest common divisor of a and b. And so last time we saw that we had the division algorithm slash theorem. This gave us a systematic way to find these pairs of numbers q and r, to write a number, say, a and b in an equation like this. So we have a systematic way of finding those numbers, and now by repeating that process again and again and again, we have a systematic way of coming to this number r sub t, which is equal to the greatest common divisor of a and b. Okay, so I realize that may be a little bit heady and theoretical looking. There's lots of notation here, so let's first look at an example of this theorem in action, and then we'll jump into the proof. So considering again our pair of integers 334 and 280, let's see what this theorem is saying to do. Well, it's saying that first you need to find a q and r so that you can write a as b times q plus r. So in this case, we'll take 343 to be our a. And we want to figure out, well, how many times does 280 go into 343? Well, 280, it's at least 200. We know that 2 times 200 is 400, so that's going to overshoot it, so it's only going to fit in once. So we get 280 multiplied by 1, and then we still need to pick up the slack. There's a remainder here. So how much is left over? How much do we have to add to 280 to get 343? That's 63. And then our process is now we take our b and we're going to move that to a left-hand side of some equation. So we're going to have 280. And it says our r becomes the new divisor. So we want to figure out how many times does 63 go into 280. So if we have 63 multiplied by 2, that's going to give us 126. And let's say we multiply that by 2, so that would be 4 times 63. That would give us 252. And, well, if I tried to add one more 63 to that, I would definitely overshoot 280. So 63 is only going to go in here 4 times, which gives us the number 252. And how much is left over? 28. And then we look at our process. What does it say? Now we take our what was involved in the multiplication over here, and that goes on the left-hand side. So now we're going to get 63 is going to be equal to 28 multiplied by some number. So how many times does 28 fit into 63? Well, 2 times 28, that gives us 56. And, well, we're not going to be able to fit another 28 in there, so it looks like that's all that's going to fit in. So we get 2 times 28 is 63 plus, well, what's missing? 56 plus 7 is what gives us 63. And then finally, we do the process one more time. So the 28 is going to come over to the left-hand side, and we're going to get 28, where now we're looking to see how many times 7 goes in, and 7 multiplied by 4 is 28. That's it. This fits in perfectly. So this is where we get a remainder of 0. And so the theorem is saying that when you get this remainder of 0, it's that r that you have in the final expression that's going to be the greatest common divisor. So in this case, it's 6. So the Euclidean algorithm is telling us that the greatest common divisor of 343 and 280 is 7. So I welcome you to try testing this for yourself. Use a calculator, see if you can find all the divisors of 343 and 280, or if you're into learning some programming, maybe write an algorithm that spits them all out and check this for yourself that this works. Or let's go through the proof, and then we'll be guaranteed to know that this process will work in every instance. For the proof of this, well, if we consider these remainders that we have here, we realize that we have this sequence b, r, r sub 1. It's strictly decreasing. And we know that all these numbers have to be greater than or equal to 0. So eventually it bottoms out. We know it has to stop somewhere. Eventually we get down to 0. And let's call the number that the first time we reach 0 going down this list, we'll say that rt plus 1, r sub t plus 1, we'll say that this is 0. And this will be the first time we encounter 0 in this list of remainders here. So what does that mean? That means that r sub t minus 1, if we think about the general form of how the relationship between these different remainders here, this tells us that r sub t minus 1 is equal to r sub t multiplied by q sub t plus 1 plus r sub t plus 1. Well, we said that r sub t plus 1 is equal to 0, so this is just equal to rt multiplied by q t plus 1. As a consequence of the Euclidean algorithm, we can also get this result, which is sometimes known as Bezout's theorem. And what this says is that if we have two integers a and b whose GCD is d, then there exists some other pair of integers, x and y, such that I can write d as ax plus by. So the proof of this relies on the Euclidean algorithm. So we're going to consider, again, the notation as it's set up on the left side of the screen with the Euclidean algorithm, which we know from the way it's written out there, we can write rt minus 2 as rt minus 1 multiplied by q sub t plus r sub t. And we know that r sub t, in particular this term, the Euclidean algorithm told us that this was the GCD of a and b. So, in other words, we could rewrite this as r sub t minus 1 multiplied by qt plus d, where this is the GCD. But then I can rearrange this equation. I can write d as r sub t minus 2 subtract r sub t minus 1 multiplied by q sub t. Now, again, from the notation of the left-hand side, we can write r sub t minus 4. This is r sub t minus 3 multiplied by q sub t minus 2 plus rt minus 2. And I can write r t minus 3 as r t minus 2 multiplied by q t minus 1 plus rt minus 1. And this allows me to rewrite rt minus 2 as rt minus 4 subtract q sub t minus 2 multiplied by r sub t minus 3, and I can rewrite r sub t minus 1 as r sub t minus 3 minus r sub t minus 2 multiplied by q sub t minus 1. Okay, so big whoop. What's the point? I'm just pushing equations around here, it seems. Well, our d is written in terms of rt minus 2 and rt minus 1. So I could replace rt minus 2 with this equation involving rt minus 4 and rt minus 3. So in other words, the index of the r is getting smaller. And same thing happens when I replace rt minus 1 with this equation expressing it in terms of rt minus 3 and rt minus 2. Again, the indices get smaller. So if we think about what's happening, we can keep rewriting d using smaller and smaller r's going up this list until eventually we have the fact that R is equal to A subtract B times Q. And so replacing all of these R's with smaller and smaller indices, eventually we'll get up to some integer combination of writing D in terms of A and B. So this does conclude the proof, but I realize this may be a little hairy and a bit hard to keep track of in your head. So again, let's return to our concrete example of 343 and 280, and let's apply this method to write 343 and 280 in some sort of integer combination that gives us 7, which is their GCD. So you're welcome to jump back in the video just to double check this is the same math, but we had figured out previously that 343 was equal to 280 times 1 plus 63, 280 was equal to 63 times 4 plus 28, and so on. Eventually we bottomed out and figured out that, at least according to the Euclidean algorithm, that 7 is the greatest common divisor of 343 and 280. So according to Bezout's theorem, we should be able to find some mysterious numbers, x and y, so that 343 times x plus 280 times y is equal to 7, their GCD. And from what we just saw, we use this sort of working backwards of Bezout's theorem. So what we're going to do is the exact same steps as the proof, but maybe this will give you a better intuition because we'll actually be working through the steps and not these abstract symbols. So we start with this second last equation. And 7 is the GCD, so we want that isolated on one side. So we know that 7 is equal to 63 subtract 28 multiplied by 2. Now we don't want to simplify anything yet because we want to use these equations to build ourselves back up to the numbers A and B. So for 63, we have this equation. The very first equation tells us how to write 63 in terms of our A and our B, 343 and 280. So I can rewrite 63 as 343 minus 280. So all I've done is just subtracted 280 from both sides of the first equation. Now 28, we see it's the remainder of the second equation that we have in our list. And so I can use this second equation to rewrite 28 as 280. So we have minus, now we're rewriting 28, so it's 280 subtract 63 multiplied by 4. And this whole thing is still multiplied by 2. Okay, so we're going to shuffle things around a bit, but remember, we don't want to simplify too much. We don't want to get rid of these numbers that are in our remainder list yet, because we're using these to work our way back up to 343 and 280. So I'm going to get here 343 minus 280. And now I'm going to distribute the minus sign into these parentheses, and I'm going to distribute this multiplication by 2 into the parentheses, but I'm not going to simplify. So I'm going to be left with 280, that is negative 280, multiplied by 2. And then this minus sign coming in changes the minus sign inside the brackets, and so this will become plus 63 multiplied by 2 times 4 is 8. Okay. So we're getting pretty close. Most of these numbers look to be in some form of 343 and 280. So I'm going to combine these 280s, so subtracting 280 and subtracting another two 280s gives me a total of 343. Subtract 280 multiplied by 3. And finally, I want to rewrite 63 in terms of 343 and 280. And again, we saw this from our very first equation, the very first setup. So 63 is equal to 343 subtract 280. Now, multiplying 8 into these parentheses, but again, not simplifying, I'm going to get 343 minus 280 multiplied by 3 plus 343 multiplied by 8 minus 280 multiplied by 8. Now I can combine some of these terms. So if I have 343 and I have 8 times 343, well, altogether I have 9 343s. So this becomes 343 multiplied by 9. And here I have negative 3 times 280, and here I have negative 8 times 280. So altogether I have negative 280 multiplied by 11. Rewriting this slightly, I get that 343 multiplied by 9 plus 280 multiplied by negative 11. Well, this is equal to what we started with on the left-hand side, 7. And so we've accomplished exactly what Bezout's theorem told us we should be able to accomplish. We found an x, namely our x in this case is 9, and a y, which in this case is negative 11, so that 343 multiplied by x, that is 343 multiplied by 9, plus 280 multiplied by y, that is 280 multiplied by negative 11, should give us 7, which is what we found to be the GCD as dictated by the Euclidean algorithm. So since this video's gotten pretty long, I think we're going to squeeze the last couple corollaries for this chapter of Dudley's book into a short video immediately following this one, and then we're going to move on to the very important sounding and the very important fundamental theorem of arithmetic. So of course, if you have any suggestions, comments, concerns, things you want to see more of, things you want to see less of, please leave them in the comments, and I'll see you in the next video.